Hello and welcome to our first video, How Computers Work Where the Rubber Hits the Road. In this video, we're going to learn some very basic computer science concepts, such as how binary numbers work, how circuits can be represented in binary, what happens when you run a program, how processors execute programs, and basic information that we need to know about memory as programmers. So now, this brings us to our first topic, which is binary numbers. So it is important to note that any number can be represented as the power of 2. As you can see, numbers like 2, 4, 8, 16, and so on and so forth are all powers of 2, and they can be represented that way. Yet, how does this work for numbers say like 1? The thing to know here is that 2 to the 0 power is 1. So if you want to represent a number like 1, you need to just do a 1 in the 2 to the 0 place. Now, computer scientists do indexing a little bit differently than most other people. So here's what happens. In this example here, we have 1 equals, it has a 3 zeros and a 1, right? We'll get to why those 3 zeros are there in a minute, but the thing to know here is like starting from the very rightmost point, this 1 here represents 2 to the 0 power. And if we go over 1, that would be 2 to the first power, 2 to the second, 2 to the third, and so on. So with our example, if we go from here just to 2 to the 0 power, we have a 1 placed here. Well, if we want to represent the number 2, what we can do is put a 2 to the first power. We put a 1 in the 2 to the first power position. Right? If we want to represent a 4, we do the same thing. We keep repeating that pattern, putting a 1 in the 2 to the second position. As you can see, just a quick recap, it's 0, 1, and 2. So that's why this one is 4. And then we repeat that pattern until you get us to number 8 by putting a 1 in the 2 to the third position. So let's say we want to represent a number like 3, 5, or 9 or something that's in the middle of these guys. What you would do in this case is you would simply, for like the number 3, you would put a 1 here. So then the number would become 0, 0, 1, 1. This is because it would have a 1 in the 2 to the 0 position, and then it would have a 1 in the 2 to the first position. So you simply would add together the numbers that are put in those places. Same thing for 5. If you want to do 5, you would have 2 to the second, which is 4, right? And then you would have a 1 in the 0 position. So if you wanted to do a number like 7, what you could do is you could have 5, but with another 1 here in the middle. So you would have 0, 1, 1, 1, which would represent 7, as that is 2 to the 0 plus 2 to the first plus 2 to the second. And now notice what happens if we have a number like 5, which is 0, 1, 1, 1, and you add a 1. All these numbers would go to 0 except for the very last one, which would kind of carry over. This is really similar to like carrying over the tens place in our number system that we normally use, which is like the base 10 number system for most of our lives, right? So let's move on to the next topic of how does a circuit represent binary. So as we learned earlier about binary numbers, we now can see that 0, 1 simply corresponds to something being on or off. So this is a really simple explanation of computer architecture. So any self-respecting computer engineer probably won't really like to hear this, but I'm going to kind of help you get a quick and dirty 10-minute computer architecture introduction, right? So circuits here are either on or they're off, right? So that's all we really care about as programmers approaching this stuff, right? So you can make a circuit that will add up together 2 binary numbers using simple on and off wires, right? That's called an ALU, and if you want to learn more about this stuff, you can take a computer architecture course or start doing some more research on the internet. But again, we don't really have the time to go through that much depth on computer architecture, but start thinking about this stuff, because like the thing that we see here in this picture is called a data path. And if you were to take a course on computer architecture, you would learn how programs can be represented as like zeros and ones and can be read in through all these different components in the data path and can actually be executed, which is kind of what we're getting to in this next slide here. So when you write a computer program, your computer code is going to be written normally at a higher level programming language, right? And then that code will get translated into zeros and ones. So depending on the language, this is done by what we call a compiler. So it's possible to write a program in zeros and ones, but trust me, you really don't want to do that. I have never done that myself, but I have written some assembly code. So what assembly is, it's about as close as we can get to writing in pure zeros and ones, and it'll have just the basic instructions that are used in programming, and those are represented through they're very short lines. I'll probably show you guys an example later, but but you should know that assembly is about as close as we can get to writing programs in pure binary, and then similarly with that, higher level programming languages are just prettier versions of writing in binary. So just like you can write a program in assembly that'll get translated directly to binary, you can then have other languages that are built on top of technologies like assembly that are a little bit higher level, and so on and so forth, which is kind of how we get to most of our modern programming languages today. So now, it's great, what the hell happens when I actually write a program, and how does the processor, how is it able to run these programs? So, as we recall earlier, programs get translated into zeros and ones, and these zeros and ones will actually represent instructions that mean something to the processor. So this all is happening in things like the program counter, which will keep track of which instruction that we are going to be executed. So as these programs are kind of compiled in zeros and ones, they'll all represent different instructions, and then the computer will go through it starting at the address that it wants, and then it will just run through all the instructions, doing the things that it should do, and kind of just keep going through them really fast. So as we get started coding, you'll quickly learn that computers are very fast in what they do, yet they're very stupid in what they do. They kind of do exactly what they tell them to do. So you need to be very careful when writing out your code, or it'll just kind of go off doing a bunch of stuff with maybe some random or kind of not really nice output. So we'll run into that later as we get more advanced in these lectures. So the next thing I want to kind of talk to you guys about is what is memory. So we have computers that we know how instructions work and how they run through, but there's no way to really kind of save our work for later and use it as we keep doing our computations. So memory does exactly that. It allows you to save your work for later and then continually use it as we go along. So memory is simply a circuit that maintains a state of input, right? At a very, very, very high level, a very high level description of the low level of memory. It's kind of a crazy example, but this is called a flip-flop actually. What happens is it has a write pin, which if you turn the write pin on, and then you're able to then set the state of that particular piece of that particular flip-flop. So if the write pin turns on, and then the state will be set to either the on or off depending on the input wires of memory. So it's kind of a complicated explanation of something that you're not really too familiar with yet, but just know that memory lets us save things for later computations, and that is temporary. So if you do something like, say, unplug your computer, your memory will kind of be wiped out since there's no more electricity keeping the circuits on. So there's a very, very quick and dirty kind of overview of basic computer science concepts, and hopefully you guys have learned quite a bit on how to kind of think about what happens when we actually write these programs. So in our next videos, we're going to actually move on with this, and we're going to use something called Scratch, and we're going to actually create a game of Pong with it. So keep watching, and I'll see you next time.